Even now, as you settle in and let the day begin to fade, something vast and unseen is passing right through you. A quiet, invisible river flowing through the walls of your room, through the very air you breathe. A silent secret the universe has kept for billions of years. This is the story of dark matter, the gentle ghost that holds our cosmos together. It is a substance entirely invisible to our eyes and to all of our instruments, and yet billions of its particles are thought to be streaming through your body every single second, unnoticed, unfelt, as you rest here tonight. This soft, continuous stream of relaxing facts about our universe is here to keep you company as you drift off. And if you find a sense of calm in learning something new before bed, a simple like or subscribe helps our quiet community grow, bringing more peaceful science to those who need to rest. Dark matter makes up about 27% of the total mass and energy of the universe. For comparison, all the familiar matter, the stars, the planets, the dust, you and me, all of it amounts to a mere 5%. The vast remainder, a staggering 68%, is an even more mysterious force called dark energy. The reason we call it dark matter is because it does not seem to emit any light at all, nor does it absorb light or even reflect it. It is utterly transparent. Its existence is known to us only through its gentle, persistent gravitational pull on the things we can see. The first person to truly suspect its presence was an astronomer named Fritz Zwicky back in the 1930s. While studying a distant gathering of galaxies called the Coma Cluster, he noticed something strange. The galaxies on the outer edges of the cluster were moving far too quickly. Based on the mass of all the visible stars and gas, their speed should have flung them away into the cosmic void, but they remained, held in a gravitational embrace far stronger than it should have been. Zwicky proposed there must be some hidden mass, which he called dunkle Materie, the German for dark matter. For a long time, his revolutionary idea was mostly overlooked by the scientific community. It wasn't until the 1970s that the idea was truly resurrected, thanks to the meticulous work of Vera Rubin. She was studying the rotation of individual spiral galaxies, and she found the same puzzle Zwicky had seen in galaxy clusters. The stars at the very edge of a galaxy's spinning disk were moving just as fast as the stars much closer to the center. This was deeply strange. According to the laws of gravity as we understood them, the outer stars should have been moving much more slowly. Her observations strongly suggested that every galaxy, including our own, was embedded in a massive, invisible sphere of this mysterious substance, a sort of cosmic halo. This dark matter halo extends far beyond the beautiful, glowing spiral arms we see in pictures, containing far more mass than the galaxy itself. What does it feel like to you, as you lie here, to imagine that so much of reality is hidden from our senses? Does it feel vast and wondrous, or perhaps a little mysterious? This quiet material doesn't seem to interact with the electromagnetic force at all. That's the force responsible for light, electricity, and magnetism, and it's why dark matter is so perfectly transparent. It also doesn't interact through the strong nuclear force, which binds atomic nuclei together. It feels the pull of gravity, of course. That's how we know it's there. And it might feel the faintest whisper of the weak nuclear force, but even that is uncertain. Because of this, we know that dark matter is not simply made of things like dim stars, cold gas, or black holes. Those things are all made from the same particles as us: protons, neutrons, and electrons, what physicists call baryonic matter. Dark matter is something else entirely. It is non-baryonic, a new kind of substance not found in our familiar periodic table. Physicists have a few leading candidates for what it could be. One of the most popular ideas is a hypothetical particle called a WIMP, which stands for Weakly Interacting Massive Particle. As their name suggests, these particles would be quite heavy, but they would interact so weakly with normal matter that they could pass through the entire Earth without touching a single atom. They are also thought to be slow-moving, which is why the prevailing theory is called the cold dark matter model. In this context, cold doesn't refer to temperature, but to their relaxed, unhurried velocity through space. This very model, known as the lambda CDM model, has become the standard framework for understanding the large-scale structure of our entire universe. Another fascinating possibility is a particle called the axion. Axions would be incredibly lightweight, far, far lighter than an electron, and were originally proposed to solve a completely different puzzle in the world of quantum physics. A third idea involves something called sterile neutrinos, hypothetical cousins to the familiar neutrinos we already know, but which interact even less with the world around them. Whatever it may be, we know that dark matter is absolutely essential for our own existence. Without its immense gravitational influence, the small fluctuations of matter after the Big Bang would never have been strong enough to clump together and form the first stars and galaxies. Dark matter provided a kind of cosmic scaffolding, a hidden framework of gravity that collected the first wisps of hydrogen and helium, allowing them to collapse and ignite. The universe would be a far emptier, more uniform place without this invisible architect. It clumps together under its own gravity, and these early clumps acted as gravitational seeds, attracting normal matter to them and sparking the creation of the beautiful galaxies we see today. When you dream, do you ever encounter things that seem to operate by their own strange, unseen rules? It's a gentle reminder that the universe can be far stranger than we imagine. One of the most beautiful ways we can see dark matter is through a phenomenon called gravitational lensing. Einstein's theory of relativity tells us that massive objects bend the fabric of space-time itself. When light from a very distant galaxy passes by a closer, massive object, like a cluster of galaxies rich in dark matter, its path is bent, just as light is bent by a glass lens. This bending distorts the image of the distant galaxy, stretching it into arcs and rings of light. By measuring the exact shape of this distortion, astronomers can calculate the total mass of the object acting as the lens. And time after time, they find the mass is far greater than all the visible matter can account for. The extra mass is the dark matter. Perhaps the most compelling evidence for this comes from a celestial object known as the Bullet Cluster. This is actually two galaxy clusters that have passed right through each other in a colossal cosmic collision. The hot gas of the two clusters, which is normal matter, smashed into itself and slowed down, creating a shockwave. But the dark matter, observed through gravitational lensing, appears to have passed right through the collision without interacting at all, just as we would expect. This separation of the gas from the gravity is considered almost direct proof that dark matter is a real, separate substance. On the grandest scales, simulations show that dark matter forms a vast, interconnected cosmic web, a network of immense filaments stretching across billions of light years. Galaxies and galaxy clusters tend to form like dewdrops along these invisible threads. The great voids between these filaments are profoundly empty, lacking both normal and dark matter. Scientists around the world are in a quiet race to finally detect a dark matter particle here on Earth. Many of these experiments are built deep underground, in old mines or beneath mountains. This immense layer of rock shields the sensitive detectors from the constant rain of cosmic rays and other radiation from space. creating a zone of profound silence where they can listen for the faintest whisper of a dark matter particle. Experiments like the Lux Zeppelin in a South Dakota mine or the Xenon experiment under a mountain in Italy use huge, pristine vats of a noble liquid like supercooled xenon. They are designed to wait patiently for a dark matter particle to happen to collide with one of the atomic nuclei in the liquid. If such an event occurred, it would produce a minuscule flash of light, a signal so faint it represents the very edge of what we can detect. So far, after years of patient listening in the dark, no definitive signal has been found. Do you find a certain comfort in the idea of these vast, invisible structures, a quiet cosmic framework holding everything we know together? Another way to search is by trying to create dark matter particles ourselves at places like the Large Hadron Collider. By smashing protons together at nearly the speed of light, physicists hope to occasionally produce a pair of dark matter particles. Because they are invisible, they would fly out of the detector unseen, but their existence would be revealed by the missing energy and momentum from the collision's aftermath. We are also searching for it indirectly. If dark matter particles are their own antiparticles, as some theories suggest, they could annihilate each other when they meet. This annihilation would produce a shower of other particles we can detect, like high-energy gamma rays. Telescopes are scanning the sky for a faint glow of these gamma rays coming from regions where dark matter should be dense, like the center of our galaxy. It's important to remember that dark matter is not the same as dark energy. While dark matter's gravity pulls things together, helping form galaxies, dark energy is a repulsive force, pushing space-time apart and causing the expansion of the universe to speed up. Dark matter clumps together, forming halos and filaments, whereas dark energy seems to be smooth and uniform, a constant pressure throughout all of space. One of the newest puzzles is that astronomers have found a few strange galaxies, like one named NGC 1052-DF2, that seem to have almost no dark matter at all. This is a profound challenge to our understanding, as we believed all galaxies needed that dark matter seed to form in the first place. The nature of dark matter remains one of the greatest unsolved mysteries in all of science. Solving it will almost certainly require us to discover new physics, something beyond our current standard model of particle physics. That celebrated model successfully describes every fundamental particle and force we know, but it simply has no candidate that fits the description of a dark matter particle. There are some alternative ideas, like modifying the theory of gravity itself, but these theories have so far struggled to explain all the observations as well as the dark matter model does. The search for this quiet secret involves thousands of scientists from countless fields, a truly global human effort to understand the universe. The total mass of dark matter in our own Milky Way galaxy is estimated to be more than 1 trillion times the mass of our Sun, and its name, dark matter, is perhaps a little misleading. A more accurate name might be invisible matter or transparent matter, since its defining quality isn't darkness, but its refusal to interact with light. Our most precise map of the early universe, the cosmic microwave background, which is the faint afterglow of the Big Bang, shows temperature patterns that perfectly match the predictions of a universe filled with the exact amount of cold dark matter we infer today. It seems this invisible substance doesn't form complex objects on its own, like dark matter stars or dark matter planets. This is because it lacks a crucial ability that normal matter has. It cannot cool down by radiating away its energy as light. Without that ability to cool and shed energy, it can never collapse into the dense, compact objects that light up our night sky. It is destined to remain a diffuse, invisible cloud, a gentle and silent presence that shapes everything, a quiet secret that surrounds you, even now, as you let go of the day and drift into sleep. As you get ready to rest, Is there one idea about dark matter that has sparked your curiosity the most? Something you might dream about tonight? It is a beautiful reminder that even in the deepest quiet of the night, we are part of something unimaginably vast and mysterious, held together by forces we are only just beginning to understand. If you enjoy falling asleep to the quiet wonders of science and would like to continue exploring the universe with us, please consider subscribing. We look forward to sharing another story with you, another time you are ready to rest. For now, just close your eyes, let the facts fade, sleep well. And so, as you settle in, letting the weight of the day gently release, we can feel the quiet pull of gravity, not just from our own world, but from the universe itself. It's a silent, invisible force that holds everything together, from the smallest moons to the grandest superclusters of galaxies. But sometimes, that pull seems stronger than it should be. A ghostly, extra gravity coming from somewhere we cannot see. The story of dark matter is really the story of listening to these echoes of missing mass. It begins, as many great cosmic mysteries do, with a single mind looking up at the sky and noticing something that just didn't seem right. In the 1930s, an astronomer named Fritz Zwicky was studying a colossal family of galaxies called the Coma Cluster. He was a brilliant, if famously cantankerous character, and as he watched these galaxies, he measured how fast they were moving. He saw them buzzing around the center of the cluster like a swarm of cosmic bees, far, far faster than they should have been. The gravity from all the visible stars and gas in those galaxies simply wasn't enough to hold on to them. The entire cluster should have flown apart millions of years ago, its members scattering into the void. Zwicky did the math again and again, but the numbers held firm. He concluded there had to be something else there, a huge amount of unseen matter, providing the extra gravitational glue. He called it dunkle materiae, or in English, dark matter. His calculations suggested that this invisible substance might outweigh all the visible stars by a staggering amount. It was an idea so strange, so profound, that for decades, the rest of the scientific world mostly ignored it. They thought his measurements must be wrong. The universe, they felt, was what we could see. But Zwicky's ghost in the machine, this echo of missing mass, lingered. If you find these relaxing facts about our universe a comforting companion as you drift toward sleep, a simple click to like or subscribe lets us know you're out there, listening in the quiet hours. It's a lovely way to support our journey together through the cosmos. The idea of dark matter waited patiently in the quiet archives of science for almost 40 years, a whisper of a theory, until another brilliant astronomer began to hear the same echo in a different corner of the sky. I wonder, have you ever held on to an idea you believed in, even when no one else seemed to understand? It takes a special kind of quiet confidence to trust what you see when the world tells you it can't be real. In the 1970s, an astronomer named Vera Rubin, alongside her colleague Kent Ford, was studying the rotation of individual spiral galaxies, like our own Milky Way. At the time, everyone expected them to spin a certain way, following the familiar laws of gravity. Stars near the dense, bright center should move quickly, while stars on the far, dim edges should move much more slowly, like the outer planets of our solar system trundling along in their vast orbits. It just made sense. The less visible matter there is, the weaker the gravity, and the slower things should move. But that is not what Vera Rubin found. As she meticulously measured the speeds of stars, she discovered something that defied all expectation. The stars on the very edge of the galaxies were moving just as fast as the stars near the center. It was as if a spinning merry-go-round had its outer horses keeping perfect pace with the inner ones, a physical impossibility without some invisible structure holding them in place. flat rotation curve, as it came to be known, was a gentle but undeniable cosmic scream. It meant that every single spiral galaxy she looked at was embedded in a massive, invisible halo of something with gravity, something dark. Her work provided the undeniable proof that Zwicky's Dunkla materia was not just an anomaly in one galaxy cluster, but a fundamental component of almost every galaxy in the universe. Yet, just like Zwicky, her revolutionary findings were met with resistance for years. Science, for all its logic, is a human endeavor, and sometimes it takes time for our minds to accept a reality far stranger than we ever imagined. Does that gentle sense of mystery ever appear in your own life? That feeling when you notice a small detail that doesn't quite add up, making you wonder what larger story is unfolding just out of sight. As the evidence for this missing mass grew, astronomers realized they could look for it in other ways. Not by searching for what it is, but by observing what it does. Albert Einstein had shown that gravity isn't just a force, but a curvature in the very fabric of space-time. A massive object, like a star or a galaxy, literally warps the space around it. And any light that passes by has to follow that curve. This means a massive object can act like a lens, bending and magnifying the light from whatever is behind it. It's an effect called gravitational lensing, a kind of cosmic mirage written in starlight. And the beautiful thing about this effect is that gravity works the same for all matter, whether we can see it or not. So, if dark matter is real, its immense gravity should also bend light. Astronomers began to see it everywhere they looked. Distant galaxies appearing warped, stretched into strange arcs and rings, their light distorted by the gravity of a massive but completely invisible object in the foreground. It was like seeing the silhouette of a ghost, not by seeing the ghost itself, but by seeing how the light from a candle behind it flickers and bends as it passes through. Have you ever been captivated by the way light plays tricks on the eyes? A shimmering heat haze on a summer road, or the beautiful distortion of a spoon in a glass of water, reminding us that what we see isn't always the whole story. The most spectacular proof of all came from an event called the Bullet Cluster. This is actually two clusters of galaxies that, over millions of years, collided and passed directly through one another. It was a cosmic event of unimaginable scale. When they collided, the vast clouds of normal, visible gas within each cluster crashed together, slowing down and creating a shockwave of superheated plasma. We can see this glowing gas with X-ray telescopes, but the dark matter, astronomers theorized, wouldn't interact with anything. It should just pass right through, like two ghosts gliding through each other. Using gravitational lensing, scientists mapped out where most of the mass in the system was, and they found it. On either side of the hot, glowing gas, they saw two massive, invisible clumps of gravity, where the dark matter had sailed through the collision completely unscathed. The visible matter was in one place, but most of the gravity was somewhere else. It was the first direct, observational proof of dark matter's existence, a perfect snapshot separating the light from the darkness. Thinking about such colossal events in the universe can sometimes bring a strange sense of calm and perspective. When you look up at the night sky, do you ever feel a sense of your own place in it all? A feeling of being both small and deeply connected? This ghostly substance isn't just a minor ingredient either. The echoes from all these different observations, from spinning galaxies to cosmic collisions, all tell us the same thing. The atoms that make up you, me, the Earth, the stars, and everything we have ever seen or touched account for only about 5% of the total mass and energy of the universe. Dark matter, this invisible gravitational scaffolding, is thought to make up about 27%. It outweighs all the familiar matter we know by more than 5 to 1. So, as you lie here, resting, letting your mind drift, remember that the universe you see is only the smallest fraction of what is actually there. We live in a cosmos filled with an invisible substance whose gravitational embrace holds our galaxy together, allowing our world to exist. It's a comforting, humbling thought that we are held in place by a mystery we are only just beginning to understand. And as you let these thoughts settle, it's perfectly fine to let your mind go, to drift into sleep, carried on these gentle currents of cosmic curiosity. If you'd like to continue this journey with us on another night, please do consider subscribing. We'll be here, ready to explore more of the quiet wonders of the universe, whenever you're ready to listen. Every star you have ever wished upon is being held in a gentle, invisible embrace, a cosmic cradle rocking softly in the silent dark. This is the story of dark matter, not as a cold, abstract problem, but as the quiet architecture of our home, the unseen arms that hold our galaxy together. It begins with a simple, almost deceptive observation when we look out into the night. We see the brilliant band of the Milky Way, a river of light splashed across the velvet blackness. We see the pinpricks of distant galaxies, swirling cities of starlight. But all that light, all that familiar, visible matter, is merely a dusting of glitter on a vast, unseen sculpture. The stars, the gas, the planets, everything we have ever known makes up only a tiny fraction of what is truly there. The rest, the overwhelming majority, is something else, something dark. Our own Milky Way, for instance, is not just the spiral of stars we see. It resides within a truly enormous, spherical cloud of this dark matter, something we call a halo. Think of the galaxy we see as the brightly lit downtown of a sprawling city at night. The halo is the entire metropolitan area, the suburbs, the countryside, stretching far out into the darkness, mostly unseen, yet fundamentally part of the whole. And if you find a sense of peace in these quiet explorations of the cosmos as you unwind, a simple click to subscribe helps us continue making them for you, creating more calming science for your bedtime listening. This dark matter halo isn't just a passive container. It is the very reason our galaxy exists as it does. Without it, our home would tear itself apart. In the 1970s, an astronomer named Vera Rubin was studying the way galaxies spin. She expected that stars on the outer edges would move much more slowly than stars near the center, just as the outer planets of our solar system orbit the Sun far more slowly than Mercury or Venus. But that's not what she found. Instead, the stars on the very fringes were moving just as fast as those further in, at speeds so high they should have been flung off into the void of intergalactic space, like children letting go of a fast-spinning merry-go-round. The only way they could be held in their orbits was if there was a tremendous amount of extra gravity, a mass that we simply could not see. This was the first strong evidence for the gravitational embrace of dark matter. It acts as a cosmic glue, a quiet, persistent force that keeps the 100 billion stars of our galaxy from flying apart. It's a comforting thought, isn't it? That our cosmic home is held so securely, protected by a force so fundamental it forms the very bedrock of structure in the universe. Does looking up at the Milky Way on a clear night ever make you feel a sense of connection to something much larger? I'd love to hear what that feeling is like for you when you find a moment to share it. This protective halo isn't just a feature of our galaxy, it is the standard for almost all galaxies. And these halos are not isolated islands. They are the brightest nodes in an even grander structure known as the cosmic web. Imagine a vast, three-dimensional spider's web stretching across the entire universe. The long, delicate threads are filaments of dark matter, and where these filaments intersect, the dark matter clumps together, forming dense halos. It is inside these halos, within these gravitational wells, that ordinary matter was able to cool, condense, and form the galaxies we see today. So galaxies aren't just scattered randomly through space. They are arranged along these invisible cosmic highways, like dewdrops clinging to the threads of a web at dawn. Dark matter, then, is not just the embrace that holds our galaxy together. It is the very scaffolding upon which the universe is built. Have you ever found comfort in the idea that there are vast, unseen structures and rules governing the universe, making it less chaotic than it seems? Let me know your thoughts when you have a quiet moment. This cosmic structure is all around us, and in a way, it is flowing through us right now as you rest. Our solar system is not stationary within the Milky Way. We are orbiting the galactic center at a speed of about 500,000 miles per hour. And as we move, we are passing through the galaxy's dark matter halo. This creates what scientists call a dark matter wind. Billions of these mysterious, invisible particles are thought to be streaming through your body, through the room you're in, through the entire planet every single second. But they are so incredibly reluctant to interact with our world that we feel nothing. It is a presence that is utterly pervasive, yet completely ghost-like. It's a silent, gentle river, flowing through everything as we drift through the night. A quiet companion on our journey through the cosmos, one that you can let pass by as you relax, as you let go of the day, feeling the safety of your own space. And yet, for all its importance, this galactic embrace holds deep puzzles that scientists are gently trying to understand. Computer simulations of how these dark matter halos should form predict that they ought to be very dense at their centers, a feature called a cusp. But when we observe real galaxies, especially smaller ones, we often find their centers have a much flatter density profile, a core. It's as if something has smoothed out the very heart of the dark matter halo. Cusp versus core problem is a delicate and beautiful mystery. It doesn't mean our ideas are wrong, but that the story of dark matter is more nuanced, more intricate than we first imagined. Perhaps dark matter particles can interact with each other in some subtle way. Or perhaps the explosive energy of star formation in the early galaxy was enough to push the dark matter around. When you're trying to fall asleep, does your mind ever wander to these kinds of gentle, unsolved puzzles? It's a relaxing way to let the day's worries fade, contemplating questions that are so much bigger than our own. Perhaps the most profound evidence for this cosmic framework comes from the faintest, most fragile galaxies we know of, the dwarf spheroidal galaxies. They are tiny, ghost-like collections of stars that orbit larger galaxies like our own. Some are so dim and sparse that they are almost impossible to see. Yet when we measure the speeds of their few stars, we find them moving far too quickly. These tiny galaxies are almost entirely made of dark matter. Some estimates suggest they contain hundreds of times more dark matter than visible matter. They are the purest examples of dark matter's influence, like little laboratories for studying its effects. They show us that dark matter is the primary ingredient, the true foundation, and the stars are just the faint light that allows us to see the shape of its embrace. Is there a particular space mystery that you find more calming than others to think about before you sleep? So, as you settle in, as you close your eyes and let my voice be a gentle guide, picture our galaxy, not as just a flat disk of stars, but as a brilliant jewel resting inside a vast, crystalline sphere of invisible matter. This sphere is holding us, guiding our path through the universe and providing the very structure that allowed our existence. It's a reminder that the most powerful and important things are often those we cannot see. A silent, steady presence in the dark. It is the galactic embrace, and you are resting safely within it, right now, as you begin to drift and dream. If you'd like to continue our quiet journey together and discover more relaxing science to help you unwind and fall asleep, I invite you to subscribe and join us again for our next exploration. And so, as the universe expanded and cooled in its infancy, a profound quietness settled over the cosmos. In that primordial darkness, long before the first star ever ignited, something else was already beginning to stir. The particles of dark matter, adrift in that silent, expanding space, felt a familiar pull, the gentle, persistent whisper of gravity. Unlike the familiar matter of our world, which was buffeted by light and energy, dark matter was immune. It was free to listen only to gravity's call. And so it began to gather. Slowly, patiently, it started to clump together, forming vast, invisible clouds that we now call dark matter halos. These were the very first structures to exist in the entire universe. They were the seeds from which everything else would eventually grow, invisible anchors in the cosmic ocean. Think of it like the first quiet thought that forms in your mind just before a dream begins, a subtle shift that sets the stage for the story to come. These halos of dark matter became gravitational wells, like gentle dips in the fabric of space-time. As the universe continued to evolve, the ordinary matter, the hydrogen and helium gas that would one day form you and me and the stars we see at night, began to feel that same gravitational pull. This gas, which had been spread out in a thin, uniform fog, started to drift. It flowed across the cosmos like a slow, silent river, drawn irresistibly toward the deepest parts of those invisible dark matter wells. It was here, cradled in the gravitational embrace of dark matter, that the very first galaxies were born. The dark matter built the framework, the silent, invisible architecture, and the luminous matter we can see simply settled into the home that had already been prepared for it. Our galaxy, and every galaxy, is a testament to this cosmic collaboration, a bright jewel set within an unseen crown. This process wasn't confined to just one location. It was happening everywhere, creating a pattern of breathtaking scale. When we map the locations of galaxies across billions of light years, we find they aren't scattered randomly like dust motes in a sunbeam. Instead, they trace out a magnificent, intricate structure, a luminous network of filaments and clusters stretching across the entire observable universe. This grand design is known as the cosmic web. It is perhaps the largest and most beautiful structure we have ever discovered. And the profound truth is that this web of light is merely tracing the underlying, invisible skeleton of dark matter that has shaped it from the very beginning. The galaxies are like dewdrops on a spider's web, revealing the gossamer threads we could never see on their own. As you settle into the quiet of your room, you can perhaps imagine this cosmic web. It has long, delicate tendrils called filaments, where dark matter is more concentrated. Galaxies are strung along these filaments like pearls on a thread. Our own Milky Way galaxy is traveling along one such filament right now. Where these filaments intersect, they form dense, brilliant knots. These are the nodes of the cosmic web, and it is here that we find the great galactic clusters, cosmic cities teeming with thousands of galaxies, all bound together by an immense concentration of dark matter. It's a comforting thought, isn't it, that even on the largest scales, the universe prefers connection over isolation. Does picturing our own small world, nestled safely within this vast, interconnected cosmic structure, bring you a sense of peace? I'd be so curious to read about the feelings these cosmic ideas bring to you as you listen and relax. between these shining filaments and bustling nodes lie the great cosmic voids. These are vast, dark, and unimaginably empty regions of space, some hundreds of millions of light years across. They are the great quiet spaces of the universe. But they are not truly empty. Even here, there is dark matter, just far, far less of it. Its gravitational influence is weaker, and so very few galaxies have been able to form in these lonely expanses. The voids are a powerful reminder that the structure of our universe is defined just as much by what is absent as by what is present. They are the deep, restful breaths between the sentences of the cosmic story, providing the contrast that makes the light of the galaxies seem all the more precious. Understanding this invisible architecture is one of the greatest challenges in modern cosmology. We cannot see it directly, so how can we be so sure of its shape? The answer lies in some of the most powerful supercomputers ever built. Scientists create vast digital universes inside these machines. They begin with a virtual box of space, filled with millions of digital particles representing dark matter and gas, and they program in the laws of physics as we know them. Then they press play and allow this simulated universe to evolve over billions of years. And time again, without fail, the dark matter particles, under the sole influence of gravity, arrange themselves into that same beautiful web-like structure. The simulations look uncannily like the real maps of our universe, giving us profound confidence that we are on the right track. It's like hearing a piece of music in your dreams and then finding the sheet music for it the next day. This invisible scaffolding does more than just guide where galaxies form. It dictates how they live and grow. Galaxies are not static. They move, they merge, they evolve, and their paths are choreographed by the gravitational currents of the dark matter web. Small galaxies flow along the filaments towards the massive clusters at the nodes, like streams flowing into a great lake. When they arrive, they can be stripped of their gas or torn apart by the immense gravity of the cluster, their stars scattered to wander between their larger neighbors. This entire dynamic cosmic ecosystem, the life cycle of galaxies themselves, is governed by the unseen landscape of dark matter on which it all plays out. And this brings us back home to our own quiet corner of the cosmos. Our Milky Way galaxy is not alone. It is itself embedded in a colossal, roughly spherical halo of dark matter. This halo is immense, stretching out more than 10 times farther than the visible, starry disk of our galaxy. If our eyes were sensitive to dark matter, the night sky would be dominated by this vast, luminous sphere, with the Milky Way just a bright ribbon at its center. This halo is our galactic protector. Its immense gravity holds our galaxy together, preventing our solar system and all the other stars from flying apart as we spin through space. It is the invisible foundation of our home. As you lie there, letting go of the day, you can feel the solidness of the bed beneath you. In the same way, our entire galaxy is resting, secure and stable, within this enormous, gentle cradle of dark matter. It's a quiet, constant presence, a source of stability in a dynamic universe, holding us safely as we continue our long, silent journey through the night. And so, while we search for it in the here and now, in deep underground laboratories and vast celestial surveys, the most profound evidence for dark matter comes not from the present day, but from a whisper, an echo from the very dawn of time. To hear it, we must let our minds drift back, further and further, past the birth of stars, past the formation of the first atoms, to a moment when the entire universe was a glowing, opaque fog. As you settle in, as you let the weight of the day begin to dissolve, allow yourself to imagine this scene. A time just under 400,000 years after the Big Bang, when the cosmos was so hot and dense that light itself was trapped, bouncing endlessly between particles in a fiery dance. But then, as the universe expanded, it cooled. And at a certain magical point, it cooled just enough for the simplest atoms to form, freeing the light that had been held captive. This first light, released all at once in every direction, has been traveling across the cosmos ever since. We can still see it today, stretched and cooled by its immense journey into a faint, gentle glow of microwaves. This is the cosmic microwave background, or CMB. It is, in the most literal sense, the afterglow of creation. It is the oldest photograph we will ever possess, a baby picture of the universe when it was an infant. And when we look at this picture, we see something extraordinary. It is almost perfectly, impossibly uniform in temperature. Almost. Scattered across this ancient light are tiny, minuscule variations, patches that are a few millionths of a degree warmer or cooler than the average. These faint ripples, these gentle temperature differences, are the seeds from which all cosmic structure grew. A slightly denser, slightly cooler patch had a little more gravitational pull, and over billions of years, it would become a galaxy. A slightly less dense, slightly warmer patch would become the empty void between them. All the magnificent clusters of galaxies, all the intricate cosmic webs we see today began as these almost imperceptible whispers in the dawn light. But here we encounter a profound cosmic puzzle, a problem that can only be solved with something invisible. According to our understanding of gravity, these tiny seeds in the early universe simply weren't strong enough. They were too small, too gentle. If only normal, visible matter existed, there would not have been enough time in the 13.8 billion years since for gravity to pull that matter together and build the vast, sprawling galaxies and clusters we now inhabit. The universe would still be a mostly uniform, thin, and lifeless soup. The growth was too fast, too efficient. It's as if the construction of our cosmic home had a secret head start. And that is where dark matter enters the story, not as a strange modern anomaly, but as the silent, foundational architect of the cosmos itself. You see, back in that early, glowing fog of a universe, normal matter, the stuff that makes up you, me, and the stars, was constantly being pushed around by the intense pressure of the trapped light. It couldn't settle down. It couldn't begin to clump together under gravity, because the radiation was always blasting it apart. But dark matter, by its very nature, doesn't interact with light. While normal matter was being tossed about in a sea of radiation, the dark matter was completely unaffected. It was a ghost in the machine, and so it could begin to collapse under its own gravity, undisturbed. Long before the first light was freed, dark matter was already gathering, forming vast, invisible pools of immense gravity. It built a hidden cosmic scaffolding, a network of gravitational wells and valleys spreading throughout the universe. It was patiently laying the foundations for a home it would never truly inhabit. Then, when the universe finally cooled and the cosmic microwave background was released, when the light pressure vanished, normal matter was suddenly free. And what did it do? It immediately began to fall into these deep gravitational wells the dark matter had already prepared. It was like water rushing into a pre-dug riverbed. This is what gave galaxy formation the enormous head start it needed. The seeds didn't have to start from scratch. They just had to settle into the cosmic cradles that had been waiting for them all along. It's a beautiful image, isn't it? An invisible architect building the foundations of our cosmic home long before the lights came on. What comforting or beautiful images does science bring to your mind as you're settling down for the night? Let me know in the comments if you feel like sharing. This beautiful story isn't just a guess, it's written into the very pattern of the cosmic microwave background itself. The specific sizes and distribution of those hot and cold spots in the baby picture of the universe can be analyzed statistically. Scientists can measure what they call the acoustic peaks in the CMB data, a name that sounds wonderfully musical for such ancient physics. These peaks tell us about the way matter and energy were oscillating, sloshing back and forth in the early universe. And the only way to make our models of those oscillations match the precise pattern we observe in the sky is to include a huge amount of non-interacting, cold dark matter. The CMB's pattern is a perfect fingerprint, and it points directly to a universe composed of about 5 times more dark matter than normal matter. It is a quiet, mathematical, but unbelievably powerful confirmation. Without this ghostly substance, the whispers from the early universe would have been too faint to ever grow into the cosmic symphony we see around us. There would be no Milky Way, no Andromeda. The night sky, if anyone were here to see it, would be a vast, dark, and lonely place, with perhaps only very small, diffuse galaxies scattered thinly across the void. The very fact that we exist, that our planet could form around a stable star inside a large, structured galaxy, is a direct consequence of the work done by dark matter in the first few 100,000 years of time. We are here because it was here first, silently shaping the cosmos for us. So, as you lie here, ready for sleep, consider that the very substance of your bed, the air you breathe, the gentle pull of gravity holding you, all owe their place in the universe to an invisible presence that set the stage. The story of dark matter isn't just a mystery to be solved, it's our own origin story. It is the quiet, unseen force that ensured the universe would be filled with structure, with beauty, and with the potential for life. It is a calming thought, knowing that the universe had a hidden plan, a secret ingredient that allowed for everything we know and love to eventually emerge from that first ancient light. The whispers are still there in that faint microwave glow, a constant, gentle reminder of the invisible architecture that holds us all. And now, you can just let that thought be. Let it drift as you drift into a peaceful and well-deserved rest. And so, we continue our journey into the quiet, invisible universe that surrounds us. A universe held together by a substance we can feel but cannot see. The hunt for this cosmic ghost, this dark matter, is one of the greatest quests in all of science. It is a search conducted not with powerful telescopes staring up into the heavens, but in the deepest, most silent places on Earth. Imagine descending, slowly, gently, far beneath the surface of the world, down past the soil, past the rock, into a profound and ancient stillness. This is where the search for a dark matter particle truly begins. The most sensitive physics experiments ever built are not in gleaming towers, but are nestled in old gold mines or beneath mountains. They are shielded by kilometers of solid rock, which acts as a natural filter, a cosmic blanket protecting them from the constant rain of particles from space known as cosmic rays. These surface particles would create a storm of false signals, a constant chatter that would drown out the one faint whisper they are hoping to hear. The quiet of the deep earth is the first necessary ingredient in listening for a ghost. If you enjoy these relaxing explorations into the quiet corners of science, a simple click on the subscribe button ensures you'll always have a calm journey waiting for you at the end of your day. The leading suspect for many years has been a hypothetical particle with a wonderfully descriptive name, the WIMP. It stands for Weakly Interacting Massive Particle. Massive because if it exists, it would have a substantial weight, at least by particle standards, perhaps heavier than a large atom. This is why its gravity is so powerful on a cosmic scale. But the key to its ghostly nature is in the first part of its name, weakly interacting. This means it rarely, if ever, bothers to notice normal matter. Billions of these WIMPs could be flowing through you, through your room, through the very core of the Earth right now as you rest here, and they would pass through as if you were nothing but empty space. They are the ultimate introverts of the universe, interacting only through the gentle force of gravity and, just maybe, one other force, the weak nuclear force. It is this infinitesimally small chance of another interaction that scientists are trying to catch. The strategy for catching such an elusive particle is called direct detection, and it is an exercise in extreme patience. It's like trying to feel a single grain of sand dropped from a great height into a vast, deep ocean. The detectors are, at their core, incredibly dense, pure, and quiet collections of atoms. Often, they are vats of a noble gas like xenon or argon, purified to an almost impossible degree and cooled until they become a clear, still liquid, colder than the most distant planet. Inside these vats, scientists wait for a dark matter particle, a WIMP, to happen to stray from its path just enough to bump directly into the nucleus of one of those xenon atoms. It's a collision that would be unimaginably rare and unbelievably gentle. If this collision were to happen, the xenon nucleus would recoil like a billiard ball struck by an invisible cue ball. This tiny jolt would disturb the electrons in the surrounding atoms, creating a minuscule flash of light, a faint, ghostly glimmer, and it would also knock a few electrons free, which would drift upwards to be collected. The combination of that first flash of light and the secondary signal from the electrons would be the telltale sign, the fingerprint of a dark matter particle finally revealing itself to our world. To detect such a subtle event, the sensors inside are more sensitive than any camera ever made, capable of seeing a single photon of light in a vast chamber of absolute darkness and stillness. Everything about these experiments must be pristine. The materials used to build the detectors, from the steel tanks to the copper wiring, are carefully selected to have the lowest possible levels of natural radioactivity. Even a tiny speck of radioactive dust from our own planet could create a flash of light that perfectly mimics a WIMP, a false positive that could send the entire scientific community down the wrong path. Some experiments use ancient lead, salvaged from Roman shipwrecks, because it has been sitting under the sea for 2,000 years, allowing much of its natural radioactivity to decay away, making it some of the most radio-pure lead on the planet. It's a beautiful thought that something lost to the depths of history could help us find something lost in the depths of the cosmos. Does the thought of these deep, silent laboratories feel calming to you, or does it spark a different kind of curiosity? It's a stillness that mirrors the quiet we seek at the end of a long day, a retreat from all the noise of the world above. For years, these incredible machines have listened in the dark. Experiments with names like Lux Zeppelin, Xenon T, and Pandax are pushing the boundaries of this technology, using larger and larger tanks of liquid xenon to increase the chances of a cosmic collision. The LZ experiment, for instance, sits nearly a mile underground in a former gold mine in South Dakota, using 10 tons of liquid xenon to wait for that one special knock. So far, they have found nothing. Not a single unambiguous signal of a WIMP has ever been confirmed. The silence from these detectors is becoming, in itself, a profound piece of data. It tells us that if WIMPs do exist, they are even more elusive, even more weakly interacting, or perhaps have a different mass than we first imagined. The ghost is proving to be even ghostlier than predicted. This profound silence has led many physicists to wonder if they have been looking for the right kind of ghost all along. Perhaps dark matter isn't a WIMP at all. This has opened the door to a whole garden of other theoretical particles, each with its own unique and strange properties. One of the most compelling alternatives is a particle called the axion. Where the WIMP is imagined as a heavy, shy bullet, the axion is thought to be incredibly light, millions or even billions of times lighter than an electron. And instead of acting like a particle, it would behave more like a vast, slow-moving wave sloshing through the universe. The entire galaxy would be filled with a sea of these axion waves, an invisible, oscillating field that we are all drifting through at this very moment. Detecting an axion requires a completely different kind of experiment. You aren't looking for a collision, but rather trying to build a kind of cosmic radio tuned to just the right frequency. The theory goes that if you place an axion field in the presence of an incredibly strong magnetic field, the axion can, on rare occasion, transform into a photon, a particle of light. The ADMX experiment, the axion dark matter experiment, does just this. It uses a powerful superconducting magnet cooled to near absolute zero to create a region where this conversion might happen. Inside the magnet is a resonant cavity, a copper-lined chamber, which is designed to amplify the signal of that one specific photon, if it ever appears. The process is like trying to tune an old radio to a very, very faint station. The physicists don't know the exact frequency, the exact mass of the axion, so they have to scan through the cosmic dial, one tiny step at a time, listening for a whisper of excess power. They tune the detector, listen in the quiet for a long, long time, and if they hear nothing, they adjust the dial by the smallest fraction and listen again. It is a slow, methodical, and deeply patient search for a single note in a silent symphony. This quest, whether for the WIMP's bump in the night or the axion's faint hum, is a beautiful reflection of our own innate curiosity. It is a search happening in the dark, in the quiet, while the world sleeps, driven by the simple, peaceful desire to understand the universe just a little bit better, to finally see the shape of the shadows. And as you let these ideas drift, feel free to let your own mind drift as well, into the quiet, dark, and peaceful realm of your own rest. And so, this gentle, invisible rain of dark matter, passing through the earth, through our homes, and even through our own bodies right now as we lie here, invites a profound and quiet question. If it is everywhere, all around us, could we ever hope to catch a single drop? Could we build a net fine enough to feel the presence of a ghost? The search for these elusive particles is one of the great undertakings of modern physics, a search that has driven humanity not to the stars, but deep, deep into the silent heart of our own planet. To listen for the faintest whisper of dark matter, we first have to escape the constant roar of the universe. Every moment, the Earth is bombarded by cosmic rays, energetic particles from the Sun and from distant supernovae. This cosmic radiation is a constant static, a background noise that would utterly drown out the delicate signal of a dark matter particle. Imagine trying to hear a single pin drop in the middle of a thunderstorm. It's an impossible task. So, to find a place quiet enough to listen, scientists use the Earth itself as a shield. They go down, deep underground, using a mile or more of solid rock to block out the cosmic noise. The journey to these laboratories is a descent into profound stillness. These sanctuaries of science are not built in pristine, sterile environments. They are often nestled within existing, operational mines or tucked away inside hollowed-out mountains. In Canada, 2 kilometers beneath the surface in an active nickel mine lies Esnolab, one of the world's deepest and cleanest laboratories. To get there, scientists put on mining gear, step into a cage-like elevator, and plunge into the earth for what must feel like an eternity. The air grows warmer. the pressure changes, and then, at the bottom, they step out into a world of bare rock before entering a hyper-clean facility, a bubble of pure science buried in ancient stone. Far across the ocean, beneath the highest peaks of the Apennine Mountains in Italy, sits the Gran Sasso National Laboratory. It's accessed not by a mine shaft, but by a highway tunnel that cuts directly through the heart of the mountain. Imagine driving through a tunnel and simply taking an exit that leads not to another city, but to a vast, cavernous hall filled with some of the most sensitive experiments ever conceived. The mountain itself provides the quiet, a massive blanket of rock absorbing the cosmic chatter from above, creating a zone of near-perfect silence for the patient vigil below. It's a beautiful thought, isn't it? That to understand the grandest structures of the cosmos, we must retreat to the quietest, most protected places on Earth. Does the idea of these silent, deep Earth laboratories feel peaceful to you? I'm curious what quiet places you think of when you're trying to unwind and let the noise of the day fade away. Inside these subterranean halls, shielded from the universe, sit the detectors. Many of the most prominent experiments are built around a beautifully simple idea. They are essentially large vats filled with a noble gas, like xenon or argon, cooled until it becomes a clear, dense liquid. The Lux Zeppelin, or LZ, experiment in South Dakota, for instance, uses a massive titanium tank containing 10 tons of ultra-pure liquid xenon. The concept is based on a game of cosmic billiards. The theory suggests that if a dark matter particle, a WIMP, were to travel through this tank, it would occasionally, very rarely, bump directly into the nucleus of a xenon atom. This collision would be an impossibly gentle one, but it would be enough. The recoiling xenon nucleus would create a tiny, almost imperceptible flash of light, a process called scintillation. It would also knock a few electrons loose, which would then be gently guided by an electric field to the top of the detector, creating a second, slightly later flash of light. By seeing these two flashes, their timing and their brightness, scientists can pinpoint where in the tank the event happened and estimate the energy of the impact. They are waiting in the dark, for years on end, just to see a pair of ghostly flickers in a bath of liquid xenon, a signal that could change our understanding of everything. The purity required for these experiments is almost beyond comprehension. The liquid xenon must be purer than anything you could imagine, because any radioactive impurity, even a few atoms, could mimic the signal they are looking for. The materials used to build the detector itself, the titanium tank, the sensors, the cables, are all meticulously selected for their low radioactivity. Every component is screened, cleaned, and handled with extreme care to avoid contamination. Even the natural radiation from the surrounding rock walls of the laboratory is a problem, so the detectors are often submerged in enormous tanks of pure water, adding another layer of shielding, another layer of quiet. It is a search for the purest signal, conducted in the purest substance, within the quietest place we can find. It's a kind of technological meditation, a long, patient listening. And it's okay if you are beginning to drift off now, letting these relaxing facts about our universe wash over you as you settle into a deeper state of rest. There's nothing you need to do but breathe and listen. Another beautiful approach uses not liquid but solid. Experiments like the Cryogenic Dark Matter Search, or CDMS, use crystals, often of silicon or germanium, that are cooled to temperatures just a sliver of a degree above absolute zero. At these impossibly cold temperatures, the atoms in the crystal are almost perfectly still. They barely vibrate at all. Here, the idea is that a passing dark matter particle would strike a nucleus and cause the entire crystal lattice to vibrate, creating a tiny pulse of heat in the form of sound waves or phonons. The detectors are so sensitive, they can measure this minuscule rise in temperature, listening for the faintest chime of a single atomic nucleus being struck. It's like listening for a single note in a symphony of silence, a vibration that signals a visitor from the invisible world. For all this effort, for all this incredible sensitivity and patience, a strange and profound silence has been the primary result. Decades of searching in these deep, quiet places have not yet yielded a definitive, unambiguous signal of a WIMP. Experiment after experiment has become more sensitive, peering deeper into the silence, only to find more silence. But this is not failure. In science, a null result is still a result. Each experiment that doesn't find a dark matter particle tells us what dark matter isn't. It rules out certain masses, certain interaction strengths. It forces us to reconsider our assumptions and to think more creatively. This quiet from the depths is a message in itself, pushing physicists to look in new places, to consider new candidates for what this mysterious substance might be. The search has narrowed the possibilities, painting a clearer picture of the ghost we are hunting. Perhaps dark matter particles are much lighter or much heavier than we first imagined. Perhaps they don't interact with atomic nuclei at all, but in some other, more subtle way we haven't yet thought to look for. The silence from these deep underground experiments is not an ending, but a redirection. It tells us the story is more complex, more interesting than our simplest theories predicted. And so, the patient vigil continues, in the quietest places on Earth, as we listen for a message from the dark. But if the message isn't arriving here, deep beneath our feet, perhaps we need to turn our gaze outward once more, back to the vast, dark spaces between the stars, where the echoes of dark matter might be ringing in a completely different way. As you settle in, letting the weight of the day begin to dissolve, think for a moment about the quiet of the night. That deep, profound silence isn't truly empty. It's filled with sounds too faint for us to hear, a distant rustle of leaves, the hum of the earth itself. On a cosmic scale, scientists are doing much the same thing. They are listening with incredible patience to the deep silence of space, hoping to hear the faintest whisper from the universe's greatest mystery, dark matter. This search for dark matter physics isn't always about seeing something new, but about learning to listen in a new way. And if you find these relaxing facts about our universe help you to unwind, a gentle click on the subscribe button ensures you'll always have a calm place to return to for your bedtime listening. We begin our journey not by looking for dark matter itself, but for its effects, the echoes it leaves behind. This is called indirect detection. It's like standing by a still lake in the dark. You can't see the stones being tossed in, but you can see the ripples they create on the surface. In the same way, we can't see dark matter particles, but we can search for the ripples, the familiar particles like photons and neutrinos that might be created when dark matter interacts with itself. One of the most compelling theories imagines that a dark matter particle can be its own antiparticle. When two of them meet, they would annihilate each other in a quiet but powerful burst of energy. This isn't a loud explosion, but a subtle release that transforms their unseen mass into things we can see. It's a process that would produce a cascade of standard particles, a faint signature tune playing constantly in the background of the cosmos. Our challenge is simply to build a radio sensitive enough to pick up that specific song. So where do we point our cosmic ears to listen for this music? We look to the places where dark matter is thought to be most densely gathered. The very center of our own Milky Way galaxy is one such place, a bustling core where the gravitational pull is immense and dark matter particles are crowded together, increasing the chances they might collide and annihilate. It's a beautiful thought, isn't it? That in the most chaotic and bright part of our galaxy, we are listening for a signal born of darkness. We also turn our attention to the small, dim satellite galaxies that orbit our own. These dwarf spheroidal galaxies are ancient and faint, but they are almost entirely dominated by dark matter. They contain very few stars, meaning there's very little astrophysical noise to get in the way. They are like cosmic quiet rooms, perfect environments for trying to isolate the faint hum of dark matter annihilation without the distraction of 1,000 other stellar conversations. It's within these quiet celestial corners that some of our most sensitive searches are focused. Is there a particular sound of the night you find most calming, a gentle hum, or a distant echo that helps you drift away? For years, astronomers using the Fermi Gamma Ray Space Telescope have detected a mysterious excess of gamma rays coming from the galactic center. This signal is puzzling. Its energy and distribution across the sky match, with remarkable precision, what many models predict we would see if dark matter were annihilating itself. For a while, it was a source of great excitement, a potential first hint of the nature of dark matter. But the universe is a complex place, and it rarely gives up its secrets so easily. Scientists now think this gamma-ray excess might have a more conventional, though still fascinating explanation. It could be the combined light of thousands of old, undiscovered pulsars, spinning neutron stars that we can't distinguish individually. The search continues, a cosmic detective story where we must rule out every other possibility before we can claim to have heard the true voice of the unseen. So we listen in other ways too. Instead of just looking for light, for gamma rays, we listen for ghosts. Neutrinos are often called ghost particles. They are incredibly light, have no electric charge, and barely interact with matter at all. Trillions of them are passing through your body right now, having traveled from the sun without you ever feeling a thing. This elusive nature is exactly what makes them a perfect messenger for dark matter physics. If dark matter annihilates deep inside the sun or in the dense galactic center, the gamma rays it produces might get stuck, absorbed by all the intervening gas and dust. But neutrinos would fly straight out, unimpeded, carrying their secret message across the cosmos directly to us. To catch them, we have to build some of the quietest places on Earth. The Ice Cube Neutrino Observatory at the South Pole is one such place. It uses a cubic kilometer of pristine Antarctic ice, burying thousands of sensors deep beneath the surface, turning the ice itself into a giant particle detector. It waits in the cold and the dark, listening for the faint flash of light a neutrino makes when it finally, rarely, bumps into an atom of ice. It's an experiment of profound stillness and patience, mirroring the very act of settling into a deep and peaceful rest. When you need to find a moment of true quiet in your day, where do you go? Is there a special place you retreat to just to listen to your own thoughts? Another channel we listen on is the stream of cosmic rays that constantly rain down on our planet. These are high-energy particles from space, mostly protons and atomic nuclei. But among them, we can find rare bits of antimatter, like positrons, the antimatter equivalent of electrons. An experiment on the International Space Station, the Alpha Magnetic Spectrometer, has been meticulously measuring these cosmic rays. It has found a surprising excess of positrons at certain energies. One possible explanation is that we are seeing the signature of dark matter annihilations happening throughout our galaxy's halo. Of course, just like with gamma rays, there are other possible sources, like nearby pulsars. The evidence is tantalizing, but not yet conclusive. And what if dark matter doesn't annihilate at all? Another beautiful idea is that dark matter particles might not be perfectly stable. Perhaps, over immense timescales far longer than the current age of the universe, they can slowly decay. If even a tiny fraction of dark matter is decaying, it would produce a faint, continuous glow of particles across the entire sky. This wouldn't be a signal concentrated in the galactic center, but a gentle, diffuse hum coming from all directions. It would be the universe's most subtle background radiation, the final, fading note of a substance that has shaped galaxies since the dawn of time. This idea of a slow decay is, in a way, very calming. It suggests a universe not of violent collisions, but of gradual transformation. A slow, graceful release of energy over eons. It's a process much like letting go of the day's worries as you prepare for sleep, allowing them to gently dissolve into the quiet of the night. What is one thought or worry from the day that you are ready to let gently decay and fade away as you settle into rest tonight? There is one search, however, that is quite literally about listening. It involves a different kind of dark matter candidate, a particle called the axion. Axions are predicted to be incredibly lightweight, and according to theory, they can be coaxed into turning into a photon of light in the presence of a very strong magnetic field. So, experiments like the Axion Dark Matter Experiment, or ADMX, are built like incredibly sensitive cosmic radios. They create a powerful magnetic field inside a resonant cavity, which is a bit like the body of a guitar, designed to amplify a very specific note. Then they listen. They listen for a single, tiny photon, a faint blip of microwave energy that would appear if an axion passed through and converted. The challenge is that we don't know the exact mass of the axion, which means we don't know the exact frequency, or note, to tune our radio to. So these experiments must slowly, painstakingly scan through all the possible frequencies. It's like turning the tuning knob on an old radio, listening through static for a clear station. The search requires almost unbelievable patience as they scan microhertz by microhertz, year after year, listening for a single, pure tone that could solve the mystery of dark matter. It's a beautiful, modern expression of an ancient human desire to listen to the quiet and find meaning in the silence. As you're listening now, what helps you tune out the noise of the day and find that perfect, quiet frequency for deep relaxation? In all these searches, in every method, there is a common thread of deep and profound patience, a willingness to sit in the quiet and just listen. Whether we are searching for a gamma-ray excess from the heart of the galaxy, the whisper of a neutrino from a block of ice, or the pure tone of an axion in a magnetic chamber, we are engaged in a form of cosmic meditation. We are tuning our senses to the subtle rhythms of the universe, trusting that if we listen carefully enough and for long enough, the unseen will eventually make itself heard. And as you let these thoughts drift, allowing your own mind to quiet down, perhaps you can feel a connection to that immense, patient search happening all around you, a search that continues even as you drift into a peaceful sleep. If you enjoy letting your mind wander through these calming science stories as you fall asleep, please do subscribe and join us again. We'll be here, ready to explore another corner of the quiet cosmos together. And so, if these particles cannot be seen directly, if they pass through us and the world we know like ghosts, how can we ever hope to prove they are there? The search for dark matter becomes a search not for the thing itself, but for its shadow, for the faintest whisper it leaves behind in the cosmos. One of the most beautiful and hopeful of these whispers is a process known as annihilation. The word sounds dramatic, perhaps even violent, but in the quiet realm of particle physics, it is more like a quiet transformation. It's the idea that if two dark matter particles drifting through the immense darkness of a galaxy's halo were to meet in just the right way, they would simply disappear. They would vanish, their mass converting perfectly into a tiny, fleeting burst of energy and other, more familiar particles. It's a beautifully simple concept governed by the most famous equation in physics. Mass becomes energy, a silent, perfect exchange. These newly born particles, the children of annihilation, are the signals we are searching for. They are the evidence we can see. Depending on the specific theory of what dark matter is, this process could release a shower of things we know how to detect: high-energy photons, which are particles of light we call gamma rays, elusive neutrinos that barely interact with anything, or even pairs of matter and antimatter, like an electron and its opposite, a positron. Each of these potential signals offers a unique way to eavesdrop on the dark matter realm, to listen for the echo of its existence. The gentle glow of annihilation is not a bright flash, but a persistent, soft hum of high-energy light emanating from the darkest corners of the universe. Of all these potential messengers, gamma rays are perhaps the most promising. Unlike charged particles, which are bent and twisted by magnetic fields as they journey across the galaxy, gamma rays travel in perfectly straight lines. They are true cosmic messengers, pointing directly back to their origin. So, if dark matter is annihilating somewhere, the gamma rays produced will travel unimpeded across millions of light years, carrying a secret message straight to our telescopes. Observing these gamma rays would be like seeing a faint lantern glowing in a distant, dark forest, telling us precisely where something hidden is located. We wouldn't see the source of the light, but we would know, without a doubt, that something was there, burning quietly in the dark. This means the best places to look for this gentle glow are the places where dark matter is thought to be most densely packed. Imagine gravity as a silent sculptor, patiently gathering these elusive particles over billions of years into vast, invisible reservoirs. The very center of our own Milky Way galaxy is one such place. Our galaxy's heart is a chaotic, crowded place, but deep within it, models predict an incredibly dense core of dark matter. It is here that we point our gamma-ray telescopes, like the Fermi Large Area Telescope, hoping to see a telltale excess of high-energy light, a signal that stands out above the known glow of stars and gas. The search is a patient one, like listening for a single, soft note in a grand cosmic symphony. And for a time, we thought we had found it. Scientists detected a mysterious, spherical haze of gamma rays emanating from the galactic center, an excess of light that didn't seem to match any known astrophysical source. This became known as the galactic center excess. For years, it was one of the most tantalizing hints of dark matter annihilation we'd ever seen. It was the right energy, the right shape, and in the right place. A soft, constant glow from the heart of our galaxy, perhaps the collective sigh of countless dark matter particles meeting their end. But the universe is wonderfully complex. More recent studies suggest this glow might be explained by a population of thousands of very old, very faint stars called pulsars, spinning rapidly and creating their own gamma rays. The mystery isn't solved. The debate continues, a quiet and careful conversation among scientists trying to interpret a whisper from 26,000 light-years away. It makes you think about all the unseen things that fill the night. When you look up at the stars, or even just close your eyes in a dark room, what hidden wonders do you imagine might be glowing just beyond your perception? I'd love to read about what your mind wanders to in those quiet moments. Because of this cosmic background noise at the galactic center, astronomers also turn their gaze to much quieter, cleaner places. They look to the dwarf spheroidal galaxies, tiny satellite galaxies that orbit our own Milky Way. These are some of the most ancient and pristine objects in the universe. They are little more than faint puffs of stars, held together by enormous, unseen halos of dark matter. In fact, they are the most dark matter-dominated structures we know of. They contain very few stars, very little gas, and almost no other confusing astrophysical processes. This makes them perfect, clean laboratories for our search. If dark matter annihilation is happening anywhere, its signals should shine brightly here, uncontaminated by the glare of other cosmic sources. Searching for annihilation signals in these tiny, dark galaxies is like looking for a firefly, not in a bustling city, but in a silent, dark field on a moonless night. Any faint flicker of unexpected light becomes profoundly significant. There is another puzzle, closer to home, that dark matter annihilation might solve. For years, instruments in space, like the Alpha Magnetic Spectrometer aboard the International Space Station, have been detecting a strange surplus of high-energy positrons, the antimatter counterparts of electrons, in the cosmic rays that constantly rain down on Earth. There seem to be far more of them at certain energies than our standard models of the galaxy can explain. Something nearby in the galaxy seems to be producing them. While spinning pulsars are again a candidate, so is dark matter. The annihilation of dark matter particles in the halo of our own galaxy could be producing these very positrons, which then wander through magnetic fields until they eventually reach our detectors. This cosmic ray puzzle is another tantalizing breadcrumb, a potential signature of dark matter's hidden life, happening all around us all the time. What makes this search even more intriguing is a subtle quantum mechanical effect. In some theories, the rate at which dark matter particles annihilate isn't constant. It can be dramatically boosted when the particles are moving very slowly relative to each other. This is known as the Sommerfeld enhancement. Think of it like a strange resonance, where two particles moving at just the right slow dance are far more likely to interact. Since dark matter particles in the cold, quiet halos of dwarf galaxies are moving very slowly, this effect could make the annihilation signal far, far brighter than we would otherwise expect. It's as if the universe is turning up the volume on this faint whisper, making it easier for us to hear, if only we know how to listen in these incredibly cold, dark places. It adds another layer of hope to the search, a chance that nature has given us a helping hand in revealing its deepest secrets. A gentle glow amplified in the stillness of the cosmic night. And so, as you settle in, as you let the day fade away, you can imagine that quiet search continuing. Telescopes pointed at the void, listening, waiting for a signal from the dark. While the great telescopes look outward, searching for the gravitational fingerprints of dark matter across entire galaxies, another search is happening in the quiet depths of our own world. Here, in laboratories shielded by kilometers of solid rock, and within the hearts of colossal machines, scientists are not just looking for shadows, they are trying to forge them. They are attempting to summon a particle that shapes the universe, yet has never been seen, to create a whisper of its presence right here on Earth. It is a search built on immense patience and profound hope, a reminder that some of the universe's greatest secrets might be revealed not in a brilliant flash, but in the quietest, most hidden of places. If you find a sense of peace in these explorations of the unknown, a simple click to like or subscribe helps share this quiet journey with others who might be looking for a calm place to rest their mind. The quest to create dark matter begins not in darkness, but in a place of unimaginable energy. Deep beneath the French and Swiss countryside lies the Large Hadron Collider, a 27-kilometer ring of superconducting magnets. Here, beams of protons are accelerated to a fraction of a hair's breadth below the speed of light. When these protons collide, they unleash a torrent of energy so immense that it briefly mimics the conditions of the universe just moments after the Big Bang. From this flash of pure energy, new particles are born, blossoming into existence according to the fundamental rules of physics. We've used this process to find known particles, like the famous Higgs boson, but the hope is that among the countless particles born in these collisions, a pair of dark matter particles might occasionally emerge, back to back, before vanishing into the unknown. But how would you ever know if you'd created something that is, by its very nature, invisible? The answer is a beautiful piece of cosmic accounting. Scientists at the collider can't see the dark matter particles themselves, but they can see everything else. They meticulously measure the energy and momentum of every single particle that flies out from the collision point. In a perfect world, everything should balance. The energy you start with must equal the energy you end with. But if, after adding everything up, there is energy and momentum missing, if the scales don't balance, it suggests that something has been created and has slipped away without a trace, carrying that missing energy with it. It would be like hearing a door open and close in an empty room. You didn't see who came and went, but you know someone was there. This missing energy signature is the ghostly footprint that physicists are searching for, a subtle imbalance that could betray the birth of a shadow. It's a bit like when you're settling into bed and you can't quite get comfortable. There's a sense that something is just slightly out of place. I wonder, what's a small, subtle detail in your own evening routine that helps you feel that sense of balance and calm before you drift off to sleep? While some try to forge dark matter and fiery collisions, others listen for its passage as it streams through our planet. The Earth is constantly moving through the galaxy's vast halo of dark matter, meaning that at any given moment, billions of these phantom particles are likely passing through your body, through your bed, and through the very center of the planet without ever slowing down. To try and catch just one of these particles in the act of interacting, scientists have gone to extraordinary lengths to create the quietest places on Earth. They have built their laboratories deep underground, in old mine shafts and beneath mountains. Places like the Snow Lab in Canada, buried 2 kilometers down, or the Gran Sasso National Laboratory in Italy, nestled under the Apennine Mountains. This extreme depth is necessary to shield their delicate instruments from the constant shower of cosmic rays and other radiation from space, which would otherwise create a storm of background noise, drowning out the faint whisper of a potential dark matter signal. Down in these subterranean sanctuaries, a profound stillness reigns, an almost perfect silence where they can wait and listen. At the heart of these quiet places lies the detector itself, a marvel of sensitivity. One of the most common approaches is the dual-phase xenon time projection chamber. It sounds complex, but at its core, it's a beautifully simple idea. Imagine a large sealed vat filled with incredibly pure liquid xenon, cooled to a frigid -100 degrees Celsius. Scientists believe that if a specific type of dark matter particle, a WIMP, were to travel through this vat, it would, on an extremely rare occasion, bump directly into the nucleus of one of the xenon atoms. This collision would be like a cosmic game of billiards on an impossibly small scale. The xenon nucleus would recoil like a struck ball, and this tiny, tiny disturbance is what the entire experiment is designed to detect. The detector is the pristine, still pond, and the scientists are watching for the faintest ripple on its surface, a sign that something unseen has just passed through. The genius of these detectors is that they are designed to see this tiny ripple in 2 different ways at once. When the xenon atom is struck, the disturbance creates 2 distinct signals. The first is an immediate, tiny flash of light, known as scintillation. It's like a microscopic spark in the dark liquid. The second signal is a small cloud of electrons knocked loose from the atom, which are then gently guided by an electric field up to the top of the detector, where they create a second, slightly delayed burst of light. By measuring the time between the first flash and the second, scientists can pinpoint exactly where in the vat the collision happened. More importantly, the ratio of the two signals, the amount of initial light versus the number of electrons, acts as a unique fingerprint. Mundane particles, like stray neutrons from the surrounding rock, create one kind of ratio. A dark matter particle is predicted to create a slightly different one. This two-signal system is a powerful tool for filtering out false alarms, allowing physicists to ignore the background chatter and focus only on the events that have the true character of a dark matter interaction. There is also a much grander, more patient way of looking for a signal. As the Earth orbits the Sun, our direction of travel through the galaxy's dark matter halo changes. For about half the year, we are moving into the stream of dark matter particles, meaning we should encounter slightly more of them, like driving into a light rain. For the other half of the year, we are moving away from the stream and should encounter slightly fewer. This should result in a subtle, seasonal variation in the number of dark matter detections, a peak in June and a valley in December. This effect is known as annual modulation. For over 2 decades, one experiment in Italy called Dama/Libra has claimed to see exactly this pattern, a rhythmic pulse that beats in time with the Earth's journey around the Sun. It remains one of the most compelling and controversial results in the field, a persistent, rhythmic signal that no other experiment has been able to confirm, leaving a beautiful and tantalizing puzzle at the heart of the search. But not all searches for dark matter involve waiting for a bump in the night. Other theories predict a different kind of particle entirely, like the incredibly lightweight axion. Searching for axions requires a completely different approach. These experiments, often called haloscopes, don't look for a collision. Instead, they try to encourage the axion to transform into something we can see, a photon of light. The theory suggests that in the presence of an extremely powerful magnetic field, an axion can spontaneously convert into a photon with a very specific frequency. So, experiments like the Axion Dark Matter Experiment, or ADMX, consist of a resonant cavity placed inside a powerful superconducting magnet cooled to near absolute zero. They then slowly and meticulously scan through different frequencies, listening for a faint, persistent hum, a tiny excess of photons at one specific frequency over and above the background noise. It is less like looking for a flash and more like tuning a cosmic radio, searching for a single, faint station, broadcasting a message from the dark universe, a whisper that could finally reveal the nature of the unseen. This patient, methodical search, a slow turn of a dial in the cosmic silence, is another face of this incredible human quest to understand the unseen architecture of everything. As we settle in, let your mind drift away from the edges of the known world, away from the familiar particles that build our chairs, our homes, and our very bodies. We've explored the standard model of particle physics, that beautiful but incomplete family of quarks, leptons, and bosons. And yet, it has no room for the universe's greatest mystery. It has no name, no place for dark matter. This means that to find it, we must journey beyond the map, into the realm of pure, wondrous possibility. It's a journey into the unseen that we take together on channels like this, providing some calm science for bedtime listening. So if you enjoy these relaxing facts as you unwind, a gentle click of the like or subscribe button is always deeply appreciated as we continue our quiet exploration. The search for dark matter invites us to imagine particles that are, in a sense, reflections of the ones we know. One of the most elegant and deeply explored ideas is called supersymmetry. It suggests that the universe has a hidden symmetry, a secret balance. For every particle we know, there exists a heavier superpartner, a kind of shadow particle. For every fermion, the particles that make up matter, there is a corresponding boson, a force-carrying particle. And for every boson, there is a fermion counterpart. It's a beautiful, poetic idea. As if the universe is a grand cosmic dance, and every dancer has a partner, moving in perfect, hidden harmony. From this dream of a supersymmetric universe emerges a leading candidate for dark matter, the neutrino. The neutrino is not a single particle, but a mixture of the superpartners of several known particles. Imagine mixing colors on a palette to create a new, unique shade. The neutrino is a quantum blend of these shadow particles. And according to the theory, the lightest of these supersymmetric particles would be perfectly stable. It couldn't decay into anything else because there is nothing lighter for it to become. It would be a true relic, left over from the very first moments of the Big Bang, a silent witness to the dawn of time. This theoretical particle has all the right qualities for dark matter. It's electrically neutral, so it doesn't interact with light, making it perfectly invisible. It interacts with other matter only through the weak nuclear force and gravity, making it ghostly and elusive. It's the perfect cosmic introvert, passing through you, through the Earth, through entire galaxies, rarely leaving so much as a whisper of its presence. It's a beautiful thought for a quiet night, that we might be surrounded by an ocean of ancient, gentle particles, completely unaware. Does the idea of a shadow particle, a perfect mirror to our own reality, remind you of any particular dream you've had? But supersymmetry is not the only path into the darkness. Another idea, born from solving a completely different puzzle in physics, gives us a candidate that is almost the polar opposite of the heavy neutralino. This particle is the axion. Axions are proposed to be extraordinarily light, perhaps 1 billion times lighter than an electron, or even more. They are so light that they behave less like individual particles and more like a vast, slow-moving wave rippling through the cosmos. If dark matter is made of axions, then our galaxy is filled with a coherent, oscillating field, a faint, silent hum on a cosmic scale. The story of the axion began not with dark matter, but with a question about the strong nuclear force, the force that binds atomic nuclei together. Physics predicted an imbalance, a certain asymmetry that we simply don't observe in experiments. To solve this, theorists proposed a new field that permeates all of space, and this field has a particle associated with it, the axion. It was named after a brand of laundry detergent because it was invented to clean up a problem in the theory. It was only later that physicists realized this incredibly light, weakly interacting particle could also be the dark matter everyone was looking for, produced in colossal numbers in the early universe. It's a lovely example of how, in science, the answer to one question can unexpectedly unlock a door to a completely different mystery. What sound do you find most calming when you're trying to fall asleep? Is it the quiet hum of a fan, or perhaps the sound of rain? The idea of a cosmic axion field is much the same, a steady, universal background note, a form of dark matter that is less of a particle and more of a presence, a gentle and persistent wave washing over everything. Then there are the whispers of even stranger possibilities. We know of neutrinos, the tiny, ghost particles that flood the universe, streaming from the sun and distant stars. They are famously shy, interacting very weakly with other matter. But what if there's a fourth kind of neutrino, one even more reclusive? This is the hypothesis of the sterile neutrino. While the 3 known neutrinos interact via the weak nuclear force, the sterile neutrino wouldn't even feel that. It would only interact through gravity. It would be a true hermit of the particle world, completely isolated from all the forces that govern our reality, save for the gentle, persistent pull of mass itself. These sterile neutrinos, if they exist and have the right mass, could have been produced in the hot, dense chaos of the early universe. They would then simply drift through cosmic history, their gravitational influence slowly herding galaxies together, forming the structures we see today, all while remaining utterly invisible and intangible to our detectors. They are a reminder that even among the most elusive particles we know, there may be levels of subtlety and hiddenness we can barely conceive of. It is perfectly all right to let these ideas just flow over you now. There is no need to hold on to them. Just allow your mind to drift on the possibilities as you relax more deeply. Thinking about these particles that barely interact with anything, does it ever feel peaceful to imagine simply observing the world from a distance without being part of the noise? Let me know your thoughts in the comments below. Perhaps the most mind-bending ideas for dark matter come not from imagining new particles in our familiar space, but from imagining new spaces themselves. String theory and other advanced models of physics suggest that our universe may have more than the 3 spatial dimensions we experience. There could be extra dimensions, curled up into shapes so tiny that we can never perceive them directly. In these theories, all the known particles of the standard model might be confined to our 3-dimensional brain, like drawings on a sheet of paper. But gravity, and perhaps dark matter, could be free to travel in these extra dimensions. Kaluza-Klein particles. If an ordinary particle, like a photon or an electron, were able to travel into one of these tiny, curled-up dimensions, it would appear to us in our 3D world as a new, much heavier particle. It would be like a note played on a guitar string. The fundamental note is the basic particle, but the higher frequency overtones, or harmonics, would be its heavier Kaluza-Klein versions. The lightest of these extra-dimensional echoes, the first harmonic of a known particle, could be stable and would interact very weakly, making it a perfect candidate for dark matter. It would be, in a sense, a familiar particle taking a shortcut through a hidden dimension. As you lie there, letting your mind wander, have you ever imagined what another dimension might feel like? It's a wonderful thought to drift away on. This idea suggests dark matter isn't a new particle at all, but a new manifestation of particles we already know, simply vibrating in a way we cannot see. It turns the search for dark matter into a search for hidden geometry, for the secret shape of space-time itself. It's a deeply profound thought that the solution to this great cosmic puzzle might not be a what, but a where. The dark matter all around us could be ordinary matter, just taking a different path, a path through a dimension folded away, as small and intricate as a dream you can't quite remember upon waking. And in that hazy space between knowing and not knowing, between seen and unseen, is a perfect place to let go and drift peacefully into the quiet of the night. And so, this dark matter, this invisible substance that holds our galaxies together, likely possesses a kind of deep, internal symmetry. It's widely believed that dark matter particles are their own antiparticles. In the world of physics, this is a beautiful and elegant idea. It means that, unlike the familiar electron, which has a positron as its opposite twin, a dark matter particle needs no counterpart. It is whole, complete, and perfectly balanced in and of itself. If 2 of these particles were to meet in just the right way, they could, in theory, simply vanish, annihilating each other and releasing a tiny whisper of energy, perhaps in the form of gamma rays. It's a concept that feels both poetic and profoundly simple, a particle that is its own beginning and its own end. Yet this process of self-annihilation is thought to be extraordinarily rare. The cosmos isn't alight with the constant flicker of dark matter particles winking out of existence. This is a testament to its profoundly delicate and non-interactive nature. The particles are spread so thinly throughout the vastness of space, and their inclination to interact, even with themselves, is so incredibly weak that such encounters are almost vanishingly improbable. Imagine walking through a gentle, silent mist where each droplet is almost totally unaware of the others. That is the universe of dark matter. It is a realm of quiet persistence, not of dramatic collisions. Its story is one of enduring presence, not of fiery transformation. As you settle into your own quiet space tonight, you can think of this cosmic ghost, passing through everything, disturbing almost nothing, content in its own solitary dance. This faint, hypothetical whisper of annihilation is precisely what many astronomers are trying to hear. It's one of the most subtle and patient searches in all of science. Telescopes, both on Earth and in space, are aimed at regions where dark matter should be at its densest, like the heart of our own Milky Way galaxy, or the cores of small satellite dwarf galaxies that orbit our own. They are listening, not for a sound, but for an excess of high-energy light, a faint glow that can't be explained by any known stars or cosmic processes. It is a search that requires immense patience, like trying to hear a single pin drop in the middle of a vast, quiet forest at night. It is a reminder that sometimes the most profound truths are not shouted, but are carried on the faintest of signals, waiting for us to become still enough to notice them. It's perfectly all right if you don't hear them tonight. It's okay to just let go and drift, letting these calming science facts wash over you as you prepare for sleep. Part of this quiet nature comes from the fact that dark matter is considered cold. When astrophysicists use the word cold here, they aren't talking about temperature in the way we feel it. They're talking about speed. In the very early universe, as everything was expanding and taking shape, dark matter particles were already moving sluggishly, drifting rather than zipping through space. This gentle, slow movement is perhaps the single most important property that allowed us to be here at all. This is the cornerstone of the leading theory, fittingly named the cold dark matter model, which has been remarkably successful at explaining the universe we see around us. This inherent coldness, this lack of cosmic haste, allowed gravity to do its work. Because the dark matter particles were moving slowly, gravity could easily gather them together. They began to clump, forming small, invisible pools of immense mass. These were the first structures to form in the entire universe. They became the gravitational seeds, the invisible scaffolding upon which everything else we see would later be built. Normal matter, the hydrogen and helium gas that would eventually form stars and planets, was drawn into these deep, dark matter wells. Galaxies, including our own Milky Way, were born inside these gentle, invisible cradles prepared for them billions of years earlier. It's a comforting thought that the universe began not with chaos alone, but with a quiet, patient gathering, a slow and steady creation of safe harbors where stars could ignite. It's in these quiet, intricate structures, the cosmic web of dark matter, that we see a pattern of immense and peaceful beauty. I wonder, have you ever found a sense of calm by noticing the delicate, complex patterns in nature? Perhaps the veins on a leaf, the frost on a window pane, or the gentle ripples on a still lake. Let me know in the comments what small, quiet patterns help you feel at peace. If dark matter had been different, if it had been hot or even warm, meaning its particles were flying about at near the speed of light, the universe today would be an unrecognizable place. These fast-moving particles would have easily escaped the gentle pull of gravity in the early universe. They would have smoothed out any small clumps before they could grow, like a wind scattering a pile of fine sand. Instead of the rich, detailed tapestry of galaxies we see, we would likely have a cosmos with far fewer small galaxies, and perhaps only giant, diffuse, blob-like structures. The intricate, web-like pattern of galactic superclusters, with its delicate filaments and vast, empty voids, is a direct signature of dark matter's calm and cool-headed demeanor. Our cosmic home is shaped by this gentle nature, a universe built for detail, for intricacy, for the existence of small, cozy corners like our own solar system. And finally, the sheer stability of dark matter is something to rest upon. For it to still make up the vast majority of matter in the universe after nearly 14 billion years, its particles must be incredibly long-lived. If dark matter particles decayed, they would have to do so over timescales far, far longer than the current age of the cosmos. They are, for all practical purposes, eternal. They are the silent, unchanging witnesses to the entire history of the universe. They were present before the first stars ignited. They watched as galaxies collided and merged, and they will likely remain long after the last stars have faded to black. There is a deep peace in that kind of endurance. As you lie here, letting the day fade away, you are surrounded by this ancient, stable presence. It is a constant, a quiet hum beneath the noise of the cosmos, a reminder that some things are built to last, to endure through the long night. Let that feeling of stability and peace guide you now as you drift deeper into rest. And so, even as our detectors fall silent, deep beneath the earth, the cosmic search continues in our minds. The journey into the heart of dark matter physics isn't just about finding something new, but about learning to be comfortable with the profound mystery that holds our universe together. It's a quiet acceptance of the unknown, much like the gentle surrender to sleep at the end of a long day. The most fundamental unanswered question, the one that whispers in the quiet moments of every cosmological thought, is simply, what is it? We have given this cosmic ghost a name, dark matter, but a name is not an identity. We have described what it does, how it sculpts galaxies and bends light, but a description of its actions is not an explanation of its nature. This remains the great, unanswered query at the core of modern physics. It's a fact about our knowledge that our greatest certainty is the depth of our uncertainty. Is it a particle, a wave, a ripple in space-time, or something so far beyond our current imagination that we haven't even learned how to ask the right question yet? It's a humbling thought to rest with that 85% of the matter in the cosmos remains a complete and utter enigma. And if we allow ourselves to imagine it as a particle, a new door of questions immediately opens. What is its mass? This isn't a small detail. The range of possibilities is staggering, spanning more than 70 orders of magnitude. It could be an ultralight particle, like the axion, so light that trillions of them could be passing through you right now. A gentle, unfelt river flowing through the very space you occupy as you rest. Or it could be a heavy, lumbering particle, a WIMP, perhaps as heavy as a gold atom, but so shy, so withdrawn, that it barely ever interacts. The search for its mass is like searching for a lost object in a field the size of a continent in the dead of night, without knowing if you're looking for a grain of sand or a heavy stone. This uncertainty itself is a truth of our current understanding, a vast, dark space in our map of reality, a perfect place for the mind to wander without needing to find a destination. There is no pressure to know the answer, simply letting the scale of the question itself be a source of wonder as you drift. This leads to another, even more intricate puzzle. Does dark matter interact with itself? We know it barely interacts with us, with our world of light and ordinary matter. But does it have its own secret life? Does it feel a force that we cannot? Some theories propose a rich and complex dark sector, a hidden universe of particles and forces that mirror our own. There could be dark photons, a form of dark light that only dark matter can see. There could be dark atoms, dark chemistry, a whole world of complexity playing out in the galactic halos, completely invisible to us. The idea that we are only seeing one half of a conversation, that the universe is home to a second, parallel ecosystem of matter, is a beautifully complex thought. It suggests the cosmos is not empty, but filled with a vibrant, hidden life. As you close your eyes, you can almost imagine it, a silent, invisible dance of dark particles swirling in the space between the stars, a secret story unfolding in the quiet of the night. And is this secret world populated by just one type of new particle or an entire family? Our own standard model of particle physics is a bustling metropolis of quarks, leptons, and bosons. It seems almost too simple to assume the dark sector would be inhabited by just a single lonely particle. So another profound unanswered question is whether dark matter is a single entity or a composite of many different particles. Perhaps there is an entire dark periodic table with its own rules, its own elements, its own kind of stability. The universe, it seems, loves complexity and variety. The possibility that the dark matter holding our galaxy together is not one thing, but a grand, diverse collection of things adds another layer of awe to the cosmos. It's a reminder that what we see, what we know, is likely just the very first page of a much, much longer story. A story you can just listen to, without needing to remember all the characters, letting the peaceful complexity wash over you. Yet even our simplest models of a single, cold, dark matter particle run into trouble when we look closely. On the grandest of scales, our theories work beautifully, predicting the cosmic web of galaxies with stunning accuracy. But when we zoom in to individual galaxies, little puzzles appear. Our models predict that the center of galaxies should have a sharp, dense cusp of dark matter. But what we observe in many galaxies is a much softer, flatter core. This discrepancy, known as the core cusp problem, is a persistent whisper that we're missing something important. It could be a clue that dark matter isn't completely cold and collisionless, that it can interact with itself just enough to spread out, smoothing its own sharp edges. It's like a footprint in the sand that doesn't quite match the suspect we have in mind. It's one of those calming scientific mysteries that scientists are patiently working on, a puzzle that is slowly being solved piece by piece across the quiet nights in observatories around the world. And amidst all these questions of its nature, a question of quantity, of cosmic balance, stands out. Why is there this specific amount of dark matter? The measurements from our telescopes and satellites tell us that for every one part of ordinary matter, the stuff of stars, planets, and people, there are roughly 5 parts of dark matter. This ratio, about 5 to 1, is a strangely specific number for the universe to settle on. Is it a pure cosmic coincidence? Or does it hint at a deep, undiscovered connection between the visible world and the dark one, a process in the early universe that created them both in this particular balance? Some theories, like supersymmetry, naturally predict a relationship like this, suggesting that the particles of our world and the particles of the dark world are two sides of the same coin. The universe seems to hold these beautiful, mysterious balances. I sometimes wonder, as you're lying here, letting your day fade away, what small, beautiful coincidences or balances have you noticed in your own life? It's a peaceful thought to hold, this idea of a hidden, underlying harmony. Finally, there's the question of the silence. If dark matter particles are their own antiparticles, as many leading theories suggest, they should occasionally collide and annihilate each other, erupting in a flash of high-energy gamma rays or other familiar particles. We have aimed our most powerful gamma-ray telescopes, like the Fermi Space Telescope, at the centers of galaxies where dark matter should be densest, listening for this faint whisper of annihilation. And for the most part, what we have found is a profound quiet. This lack of a clear signal is not a failure, but a crucial piece of information. It tells us what dark matter is not. It rules out many of the simpler, heavier WIMP models. The silence from the heart of the galaxy is its own kind of answer. It's a calm, steady truth that pushes us to think in new directions, to listen more carefully, and to consider possibilities that are more subtle, more elusive, and perhaps even more wonderful than we ever imagined. The universe is not shouting its secrets, it is whispering them, and we are just learning how to listen in the quiet. And so, while we search for what this substance is, we can also look up and see what it has already done. The universe we see, the glittering tapestry of galaxies against the velvet black, is not the universe as it began. It is a universe that has been sculpted, shaped, and guided by an unseen hand. Dark matter, it turns out, is not just a passive passenger in the cosmos. It is the quiet architect, the patient shepherd of cosmic evolution. In the very beginning, moments after the Big Bang, the universe was an almost perfectly smooth, hot, dense soup. But almost is the key. There were minuscule, quantum-scale fluctuations in density, tiny ripples in the fabric of space-time. In the ordinary matter, these ripples were smoothed out by the intense pressure of light and radiation. But dark matter felt none of that. It was free to listen only to the whisper of gravity. And so, where there was slightly more dark matter, gravity pulled in a little more. These tiny, over-dense seeds of dark matter were the very first things to begin collapsing, growing silently in the primordial fog long before the first atoms could even form. They were the invisible foundations upon which everything else would later be built. As these seeds of dark matter grew over hundreds of millions of years, they didn't form isolated clumps. Instead, gravity pulled them into a vast, interconnected network of filaments and walls, surrounding enormous, empty regions we call cosmic voids. This is the cosmic web, the largest known structure in the universe. It is an immense, invisible skeleton, and the galaxies we see are like faint lights strung along its gossamer threads. This structure arose naturally from the patient, persistent pull of dark matter gravity over billions of years. The bright, luminous matter of stars and gas was simply pulled along for the ride, flowing like rivers into the deep gravitational valleys carved out by the dark matter, eventually lighting up to reveal the underlying architecture. What we see when we map the universe is not a random scattering of galaxies, but the glowing outline of a hidden cosmic scaffolding that has been there all along. As you picture this immense, quiet structure built in silence over eons, does it change how you feel about the night sky? I'd love to hear what thoughts or feelings come to mind for you in the comments below. Every single galaxy, including our own beautiful Milky Way, is thought to reside inside one of these dark matter structures. We believe we are nestled within a vast, roughly spherical cloud of dark matter known as a halo. This halo is enormous, perhaps 10 times wider than the visible spiral of stars we see. It's a gravitational cocoon that holds our galaxy together, preventing our fast-moving outer stars from flying off into the void. The galaxy didn't attract the halo, it was the other way around. The dark matter halo formed first, a massive, invisible gravitational well, and ordinary gas was then pulled into its center, where it cooled, condensed, and eventually ignited into the starry disk we call home. Our galaxy is just the luminous jewel at the heart of a much larger, darker, and more mysterious treasure chest. And the shape and history of that dark matter halo may have even dictated what kind of galaxy we became. Some theories suggest that the amount of spin a primordial dark matter halo had could influence whether a flat, spinning disk galaxy like ours formed, or a more chaotic, spherical one known as an elliptical galaxy. Halos that were rotating more slowly might have allowed gas to fall in from all directions, creating a disorganized jumble of stars. Faster spinning halos, on the other hand, would have encouraged the gas to settle into a stable, spinning disk, just like a potter's wheel shaping clay. The very form of these cosmic cities of light may be a direct consequence of the invisible dynamics of their dark matter hosts. It's a wonderfully calming thought, isn't it? That even on these scales, there is a quiet, underlying order guiding the chaos into beautiful, familiar shapes. It's okay if your mind is beginning to drift with these thoughts. Letting them wash over you is part of the journey. Just relax and let the universe unfold. If you want to see this principle in its most extreme form, you can look to the smallest galaxies. The universe is filled with tiny, faint dwarf galaxies, some with only a few thousand stars. And what's fascinating is that these little galaxies are utterly dominated by dark matter. For every one part of visible matter, there can be hundreds or even thousands of parts of dark matter. They are less like galaxies and more like tiny, fluffy clouds of dark matter that happen to have a few stars sprinkled within them. These ghostly little systems are some of the most ancient objects in the cosmos, cosmic fossils that have been orbiting larger galaxies like our own for billions of years. Because they are so simple and so dark matter rich, they are one of our best laboratories for studying its nature, for trying to catch a glimpse of the invisible substance that holds them together. Thinking about these ancient, quiet processes can be so soothing as the day winds down. What's one other science topic you find particularly relaxing to listen to as you get ready for sleep? Feel free to share it below. The existence of these dark matter clumps was not just important, it was essential for our very existence. In the early universe, after it cooled enough for atoms to form, there was a period known as the Cosmic Dark Ages. The universe was filled with neutral hydrogen gas, but there were no stars to light it up. It was dark, silent, and empty of structure. For ordinary matter to collapse into a star, it needed a deep enough gravitational well to fall into. On its own, it would have taken an incredibly long time, but the dark matter halos were already there, waiting. They had been patiently growing for hundreds of millions of years. When the ordinary gas eventually felt their pull, it had a pre-made gravitational cradle to fall into. This dramatically sped up the process, allowing the gas to become dense enough to ignite the first stars and end the cosmic dark ages. Dark matter, in essence, set the cosmic clock for when the lights in the universe would finally turn on. And this grand cosmic evolution, guided by dark matter, is still happening right now, just on timescales too slow for us to perceive. The cosmic web is not static. Over billions of more years, gravity will continue its slow and patient work. The filaments of the web will continue to channel galaxies and gas into the great intersections where galaxy clusters reside. These clusters, the largest gravitationally bound objects in the universe, will continue to grow larger and more massive. And the great cosmic voids, already so incomprehensibly vast, will grow even emptier as the matter on their edges is slowly pulled away onto the surrounding filaments. The universe is becoming more structured, more defined in its contrast between the crowded, bright highways and the silent, dark emptiness. It is a future being written by the silent, invisible ink of dark matter's gravity, a story unfolding with a patience that we, in our fleeting lives, can only marvel at as we drift off to sleep. As our long journey through the cosmos comes to a gentle close, we find ourselves standing at the edge of a great, quiet ocean, the ocean of what is yet to be discovered. The story of dark matter is not one with an ending, but one with a peaceful, ever-receding horizon, inviting us forward into the calm of the unknown. And as you settle in tonight, letting the day dissolve, we can walk toward that horizon together, one last time. This ongoing, quiet search for the universe's missing pieces is one of the most profound stories of our time. And if this exploration of dark matter physics helps you unwind, a simple click on the like and subscribe buttons helps our channel reach others who are also looking for a peaceful place to rest their mind. The search for dark matter now is a study in patience, a global meditation on a single unifying question. And the next chapter of this search will be written deep underground, in laboratories quieter than any place on Earth's surface. The next generation of direct detection experiments are being designed on a scale that is simply breathtaking. Projects like the Darwin Observatory plan to use immense, multi-ton vats of purified liquid xenon, creating a target for dark matter particles so vast that if a WIMP is out there, passing through us right now, its chances of finally leaving a trace will be higher than ever before. It's like building a larger, more sensitive net to catch the most elusive fish in a cosmic sea, hoping for that one tiny, telltale ripple in the stillness. But the future of this search isn't just about looking deeper underground. It's also about looking further and with clearer eyes into the heavens. Future space observatories, like the magnificent Nancy Grace Roman Space Telescope, are designed to be dark matter mappers on a cosmic scale. With an infrared view 100 times wider than Hubble's, this telescope will chart the precise locations of billions of galaxies. By measuring how their light is subtly bent and distorted by the gravity of things we cannot see, it will create a map of the universe's invisible architecture with such stunning precision that it might reveal the very nature of dark matter particles themselves, not by seeing them, but by seeing the grand, graceful way they shape the universe around them. What a beautiful thought to drift off to. The idea of a telescope mapping the invisible. I wonder, what's the most peaceful image your mind has ever conjured up right before sleep? At the same time, many scientists are now looking beyond the most popular theories, listening for something entirely different. The search is expanding to include possibilities once considered exotic, like the axion, an incredibly light, ghostly particle. Future experiments designed to find axions don't look for a collision, but rather listen for a conversion. In the presence of an immensely powerful magnetic field, an axion could, in theory, transform into a faint flicker of light, a single photon. These experiments are less like particle detectors and more like enormous, exquisitely sensitive cosmic radio receivers, slowly tuning their dials through the frequencies of the universe, listening for a faint, persistent hum from the dark sector, a whisper that would finally tell us we are not alone in the matter of the universe. Listening for a whisper from the universe? It's a form of patience we can all learn from. Do you find that listening to these calm facts helps quiet the noise of your own day? And of course, the great particle accelerators continue their own unique search. The future for the Large Hadron Collider involves an upgrade to what's called high luminosity. This means it will be creating trillions upon trillions of particle collisions, an amount of data so vast it's difficult to comprehend. In this storm of energy, scientists will again search for the ghost in the machine. They will look for collisions where particles of dark matter might be forged, flying away from the impact site without a trace. Their existence would be inferred only by an imbalance, a signature of missing energy and momentum that has vanished from the detector, carried away into the invisible realm. It's a profound and difficult search, looking for something based on the empty space it leaves behind. It feels increasingly likely that the final answer won't arrive like a thunderclap from a single experiment. The ultimate discovery of dark matter may instead be a slow, quiet dawn. It might come from the careful, meticulous weaving together of threads from many different searches. Perhaps a faint signal from a detector deep underground will perfectly match a subtle anomaly in the cosmic microwave background, which in turn corresponds perfectly with the amount of missing energy seen at the LHC. The truth might reveal itself not in one loud voice, but in a harmonious chorus of whispers, all singing the same quiet song from different corners of science. A convergence of evidence so powerful it becomes undeniable. It's a reminder that sometimes the most complex puzzles are solved not with one loud answer, but with many quiet confirmations. Is there a simple, recurring thought or feeling that brings you comfort as you get ready for bed? And perhaps the most beautiful fact of all in this grand pursuit is how it has united us. The global scientific effort to understand dark matter is one of the most profoundly peaceful and collaborative ventures in human history. It brings together thousands of brilliant minds from dozens of nations, all sharing their knowledge, their technology, and their dreams. In a world so often divided, these massive, multi-generational projects are a testament to what we can achieve when we focus on a shared curiosity, a common wonder about the universe we inhabit. It is a quiet, hopeful model for human cooperation, driven by nothing more than the desire to understand. And this leads us to our final thought for this journey. Even if a definitive dark matter particle is never found in our lifetime, the pursuit itself has already changed the world. This quest has pushed our technology to its absolute limits, leading to innovations in computing, material science, and imaging that benefit all of humanity. It has deepened our understanding of gravity, of cosmology, and of the very history of our universe. It has taught us humility, reminding us that 95% of reality may lie beyond our senses. The enduring value of this great scientific mystery may not just be in finding the answer, but in the incredible journey of the search. A search that inspires us to be more curious, more collaborative, and more at peace with the magnificent unknown. A journey with no certain end, much like the journey into our own dreams each night. As we come to the end of our own exploration of these facts, what has been the most surprising thing you've learned about this invisible universe? As the gentle pull of sleep beckons, let your mind rest in that peaceful uncertainty. The universe will continue its silent cosmic dance, held together by forces we are only just beginning to comprehend. And the people who search for those answers will continue their patient, hopeful work, content in their pursuit. It is okay to let go now. It is okay to release the questions and simply float in the vast, dark, and beautiful quiet. Let the mysteries of the cosmos become a gentle lullaby, a reminder that there is so much more to wonder about tomorrow. Thank you for sharing this quiet time. If you'd like to continue our peaceful explorations and find more relaxing science to fall asleep to, I hope you'll subscribe and join us again for another journey into the calm corners of knowledge. Until then, sleep well.